Number 1. Suppose you wanted to determine whether students who close their eyes are better able to estimate when 30 seconds have passed than students who do not close their eyes. So we ask students to tell you when to stop a stopwatch after they think 30 seconds have passed. You find the first 50 students arriving at school one day. For those 50, you flip a coin to decide whether or not they will close their eyes during the test. Then you compare the amounts by which each group overestimated or underestimated. Does this study use random sampling? So did we take a random sample here? So we took the first 50 students arriving at school. That is not a random sample. No, this is not a random sample. Everyone didn't have an equal chance of getting selected. Only those first 50 people got picked. Everyone else then could not get picked. So this is not a random sample. Why do we use random samples? We use random samples to get, we use samples. We use random samples. We use random samples to get a representative sample for the population. We want everyone to have an equally likely chance of getting selected. And in this case, if you're not an early riser, if you don't wake up early and get to school early, you will not get picked. So we use random samples to get a representative sample from the population. This case, it's not. We just took the first 50 and called it a day. Did this study make use of random assignment? Did this make use of random assignment to assigning them to two groups? Yes, it did. It did make use of random assignment. Yes, the coin flipping was random. The coin flipping determined their group. Determined the treatment. That coin flipping was the random assignment, and whether, depending on, that told them which treatment they got. Random assignment gives us cause and effect. Random assignment gives us cause and effect. Gives us a cause and effect relationship. So whenever we're conducting an experiment, in this case is, which we're going to answer in the next question, whenever we conduct an experiment, we want to randomly assign them to the two groups so that we can conclude that we have a cause and effect relationship. That way, that random assignment will reduce the bias between the two groups. Randomness took care of who's in what group. There is no influence of the researcher deciding what ended up in which group. So do we describe this as an observational study or an experimental study? This is definitely experimental because treatments were being applied. Because treatments were applied. You kind of had the control group of people who didn't close their eyes versus the treatment group where they got the treatment of closing their eyes. Random assignment was used, which is huge. Random assignment is key with experiments. And then we need to compare the results at the end. So this is definitely an experiment because we had those treatments. We weren't just sitting there, standing there, watching how long people counted to 30 seconds, how long people thought 30 seconds was. There was some actual treatments being applied here. Number 2, the manager of a food service at a local high school is interested in assessing students' opinion about a new lunch menu for the school cafeteria. The manager is planning to conduct a sample survey of the student population. Which of the listed methods of sample selection would be the most effective at reducing bias? I don't want any bias in my sample here. I want a representative sample of the population. Randomly select one day of the week and then select the first 30 students who enter the cafeteria on that day. That sounds like a terrible idea. Why? Because you're only taking the first 30 students. That's pretty bad. And also, you're only asking kids who are in the cafeteria. They're the kids who want to go eat lunch. They probably like the school lunch. So they're going to have strong opinions about the changes to the menu. That's not going to be a representative sample of the entire school population. First, post the survey on the school website and use the first 30 surveys. Again, that first 30 that first 30 is a bad idea again. And if you post it on a website, there's going to be this volunteer response bias where the people who have really, really strong opinions are going to go fill out that survey, and the people who really don't care aren't going to take the time to go to the website and fill out the survey. So that's definitely not a good option. Randomly select 30 students from a list of all the students in a school. That seems very basic, but that seems like a really, really good choice to just randomly pick 30 students from the list of everyone at the school. Let's see what's wrong with number 4. Randomly select one classroom in the school, and then select the first 30 students who enter that classroom. That is not a good choice because once you select that classroom, everyone doesn't have an equally likely shot of getting picked. Once you just pick a classroom, you've limited the population down. You're not going to pick from everyone who goes to the entire school. And again, that first 30 idea is still not settling because you want to get a representative sample, not just the first people who show up. The manager wants to know if a student's gender is related to the student's opinion on the menu. What statement best describes this study? So is this an experiment or is this an observational study? Well, if this was an experiment, there would have to be some kind of treatment. We were assigning this student to, we'd have to apply a treatment here, and I don't see how we can apply a treatment of you are male and you are female. So this is just going to be an observational study because we're just observing the relationship between gender and their opinion. We're not actually doing anything to influence that. Because it's an observational study, will I be able to establish cause and effect? No, I cannot do cause and effect. I cannot get cause and effect relationships from observational studies. That only comes from experiments. Number 3. A circular spinner is divided into 5 equal sectors of different colors. A student spun the arrow of the spinner 200 times and it landed and recorded the arrow stopped in the orange sector about 26 times out of 200. So we have a spinner here. We have 5 equal sectors. 1, 2, 3, 5. Pretend those are all equal. Let's try that again. Let's make this 5 and make them all equal. And apparently one of them is orange. One of these sectors, and remember all these sectors are equal, so the probability of landing on any sector is equal. We have one orange, one there. To test whether the spinner was fair, the student used a computer to simulate the number of times the arrow stops on orange in 200 spins of a fair spinner equally divided into 5 sectors. So they assumed it was fair. This was assuming the spinner was fair. Which makes sense that it's centered around 40 because I would expect it to be 40 times out of those 200. So we had a sample of 26 out of 200 times. So if I go down to my distribution here, 26 we can say is just that little guy right there. 26 is very, very extreme. It's very far away from the mean. Based on the results of the simulation, the student concluded there is statistical evidence that the spinner is not fair. Explain why using statistical evidence why the student is correct. Well, that outcome only happened 5 times. 5 times out of there's clearly a lot of simulations here, 80, 70. So this simulation occurred only 5 times. Getting 26 oranges or less oranges occurred only 5 times out of this. I'd say there's probably 1,000 or 500 simulations here. This event is very unusual. Usual, assuming the spinner was fair. We conclude the spinner's not fair. We say it's not fair because assuming it was fair, this event did not happen that often at all. So therefore we're going to say it's not a fair spinner because assuming it was fair, things didn't work out for us, so we're going to say it's not fair. Since the student decided the spinner was not fair, the student wanted to investigate the true probability or the true proportion of spinning an orange. So recall that the student spun it 200 times, or 26 of those stopped on the orange sector. What's our p-hat? What's our sample proportion here? Our sample proportion is 26 out of 200, which is about 13% or 0.13. So we have a sample proportion of 0.13. Assuming the sample proportion, so we assume that the sample proportion was true. Assuming the sample proportion was the true population proportion, a simulation of spinning the spinner 200 times was done 500 times, and below is the distribution. So each dot here is a sample, each dot is a p-hat, each dot is a sample proportion from 200 spins. So we assumed it was 13%, which is why it's centered around 13, our sample proportion. And we're going to use that to construct a confidence interval. So what's my margin of error? My margin of error is 2 standard deviations of the sampling distribution, which comes out to 0.048. Construct a 95% confidence interval and interpret its meaning. So a confidence interval is the plausible values for the true population parameter. So to make our confidence interval, we use the mean of our sampling distribution, which in this case is 0.128. So we do 0.128 plus or minus 2 standard deviations, or plus or minus our margin of error. So when I add that on, what interval do I get? My interval, first let's subtract to get our lower bound. That gives me 0.08, 8% to 0.176%. What does that confidence interval mean? That's my confidence interval there, from 0.08 to 0.176. We are 95% confident that the true population proportion of spinning an orange is between 8% and 17.6%. So this range here represents plausible values. That represents plausible values for the population proportion. Our P, our plain old P. So that we're 95% confident that our population proportion falls between 8% and 17.6%. Our friend Julie believes that the true proportion of spinning an orange is 16%. Use statistical evidence to support or refute Julie's claim. Well, once we have this confidence interval, we need to ask ourselves, is the given value in the confidence interval or does it fall outside the interval? 16% is in the interval. 16% is in our confidence interval. Well, the values in the interval are plausible values for the population proportion, because our confidence interval represents plausible values for the population proportion. Julie's 16% is a possible true proportion. It is a possible population proportion. 16% is in our confidence interval. That's our statistical evidence. It fell in our confidence interval. And because the confidence interval is plausible values for the population proportion, Julie's 16% is a possible proportion. She thought it was 16%. Our confidence interval supports that. Number 4, a randomized controlled experiment compared the reaction time in milliseconds for subjects who had been sleep deprived in group 1 and subjects who have not in group 2. So we have the dot plots of sleep deprived in group 1, not in group 2, and we see that their scores are a little bit higher than the people who actually got to sleep in group 2. Calculate the difference of sample means x bar 1 minus x bar 2 and interpret its meaning. So we need to calculate our means here. We need to calculate the mean for group 1, and we need to calculate the mean for group 2. And the way that we're going to do that is you're going to take this dot plot and type the data into your calculator. 6, 8, 10, 11, 11, 12, 13, 13, 14. Go through and type this data into your calculator, do 1var stats to get your mean, and for group 1, you're going to get 14.38. And if you repeat that same process for group 2, you're going to get a sample mean of 9.5. So when we compute the difference of sample means, I'm going to do x bar 1 minus x bar 2. I'm going to do 14.38 minus 9.5. 14.38 minus 9.5 gives me a difference of 4.88. What does that 4.88 represent? What is the meaning of this difference of sample means? So what this difference means is the mean reaction time for group 1, which is the sleep-deprived people, is 4.88 milliseconds longer or greater than the mean reaction time for group 2. So the mean reaction time for group 1 is 4.88 milliseconds longer or greater than the mean reaction time for group 2. We should be able to quickly interpret the difference of sample means. Who's bigger by how much, and make sure you're using the words mean and have the units in there. The graph below shows the results of 100 repetitions of a simulation to investigate. I believe this is 500, not 100. 500 repetitions of a simulation to investigate the difference in sample means when there is no real difference in the treatment groups. Use the graph to determine whether the observed mean reaction time for group 1 is significantly larger than the observed mean reaction time for group 2. So now that I have this diff of 4.88, I'm going to go to my graph and find 4.88. 4.88 is all the way out here. I want to know what diffs were bigger than 4.88. So the probability that my difference is bigger than or equal to 4.88, well, there's only one dot, 1 out of 500 times. 1 out of 500 times is 0.2%. 0.002, which is 0.2%. There's a 0.2% chance of getting that difference. So how did we get this dot plot? We assumed there was no difference. We assumed there was no difference. Then we scrambled the groups up, found the difference of sample means, and plotted those. The probability of getting a difference of sample means that's bigger than or equal to 4.8 is approximately 0.2%. So we can say our difference of sample means is statistically significant. Is statistically significant as the probability of obtaining a difference this extreme or more assuming there was no difference there is no difference is only 0.2%. This did not happen by chance. This did not happen by chance. So, big picture here. We found our difference and it happened 0.2% of the time. So we can say our difference of sample means is statistically significant, as the probability of obtaining a difference this extreme or more, assuming that there was no difference, is only 0.2%. This didn't happen by chance, something was going on here. Can we conclude that sleep deprivation caused this difference? We can imply causation here. Yes, we can say it caused, we can say it caused this difference because we conducted an experiment. And what was nice about this experiment that had a control group and treatments that were randomly assigned. Those are the two features of experiments. We have a control group and treatments that are randomly assigned. So, overviewing the difference of sample means, you find your difference of sample means, you find it on the re-randomization simulation, and you find how many dots are more extreme than that. How many are bigger, or if you're over here, how many are less than that sample mean, that difference of sample means. And then you can say that sample mean is statistically significant if that probability is less than 5%. In this case, we were much less than 5%. We were only 0.2%. So we say the probability of attaining a difference this extreme or more extreme, assuming that there was no difference, is only 0.2%. When we say assuming there's no differences, we're saying this didn't happen by chance. Something was making this happen, and we can actually have a causation here. We can actually conclude with causation because we conducted a randomized and controlled experiment.